This is tutorial 7, looking at question number 1 in the section on viscous effects. In this question, it goes as follows. A thrust bearing fitted at the one end of a rotating shaft has the following specifications. A thrust bearing is a bearing that has an end force on the shaft and a linear force along the axis of the shaft. So the outer diameter of the bearing surface is 200 millimeters, the inner is 80 millimeters. So the shaft's rotating at 300 revs per minute. We have the oil kinematic viscosity and density and thickness given, and that is the oil that is between the rotating shaft and the stationary surface. So the first question is to derive an equation from first principles with the aid of a clearly labeled sketch to calculate the torque required to overcome fluid friction of thrust bearing. So below the question you can see I've drawn a diagram illustrating what the bearing looks like, and below that I've also drawn a diagram to show the end of the bearing. Looking at it from the end, you have the outer radius, the inner radius, and then you have a radius, an arbitrary radius to a thin element at radius r, and the element is dr thick. So we're going to use that in our derivation. So we know that torque equals force times radius. We're going to consider the elemental strip. dr at a radius of r. So torque is equal to shear stress times area times the radius, because our shear stress is equal to a force divided by an area. So therefore torque is equal to the shear stress, which is rho, and then times your kinematic viscosity, omega r over t, and that is multiplied by 2 pi r dr, which is your area, and that is multiplied by the radius. Therefore torque is equal to 2 pi rho nu omega over t, and now we're going to integrate between r1 and r2. R cubed dr. So our torque is equal to pi rho nu omega over 2t after integrating, and now we have r to the 4 and the limit r1 and r2. We know that omega is 2 pi n over 60. We also know that R1 is equal to 0.1 meters and R2 is equal to 0.04 meters. That's given to us. So we substitute into our torque formula. Is pi times 880, which is rho times 220 nu times 10 to the minus 6, and that's all over 2 times T 0.02 times 10 to the minus 3. That's the thickness of the oil, multiplied by 2 times pi times 3000, which is N over 60, multiplied by R 0.1 to the 4 minus R at 0.04 to the power 4, and that gives us a torque of 465.46 Newton meters. Alright, that is the end of the first question. Second question, calculate the power absorbed by the thrust bearing. Power, we can calculate taking the torque and times omega, T omega, which is the angular velocity. So that's 465.46 multiplied by 2 pi 3000 over 60, and that gives us a power of 146.228 kilowatts. The third question is calculate the terminal velocity in meter per second of a block with mass 1 kilogram and a contact area of 1 square meter sliding down an incline of 1 in 100 on a film of water with a film thickness of 0.1 times 10 to the minus 3 meters and a dynamic viscosity of 1 times 10 to the minus 3. Alright, so this is a totally independent question. Right, so the mass of the block is 1 kilogram. The slope is 1 in 100. Kinematic viscosity 1 times 10 to the minus 3 kilogram per meter second. The area is 1 square meters. The thickness of the film of water is 1 times 10 to the minus 4 meters. So if we take 1 over 100, we can say theta, the angle of the slope, is arctan 1 over 100, which is equal to 0.5729 degrees. Okay. Okay, let me just draw a diagram. We have a slope of theta degrees. We have a block. And we have some water. We have a force of mg sine theta. Bring it down the slope, and mg cos theta. Bring it towards the surface, and this would be mg. Alright, so mg sine theta is equal to mu v over t times area so 9,81 sine theta is equal to 1 times 10 to the minus 3 over 1 times 10 to the minus 4 times v times 1. So that leaves us with a velocity of 0,00989 meters per second. And that is the end of the problem.